We need the claps.
Good afternoon, everyone. My name is Rituraj Jodha. I work as a data scientist for Microsoft and work on building solutions to solve the cybersecurity challenges. So let's start with a quick show of hands. How many of you heard or given this advice that never share your password with anyone? Now, what if I tell you the attacker does not need your password to access your emails? No phishing for credentials, no malware, all they just need one click, your consent. You all must have seen a screen like this. Whenever you see these screens, the applications hosted on the cloud or the websites behind these screens are basically requesting permissions to access certain parts of your data. Now, the data could be your profile picture, your name, your email address, and in some cases, it could be your calendar or your email. Now, when you click on the accept, basically you are granting the consent to these applications to go ahead and access those resources on your behalf. Now, imagine if those cloud applications or website are not created by a legitimate developer, but by an attacker. Let's see how it can happen. So let's say an employee gets an email with the title, "A file has been shared," or "Your document is ready." It contains a link, and when an employee clicks on that link, it will lead to a consent screen like this. Now, these consent screens looks quite normal, and these applications could display a friendly name. They can have a logo of a reputed publisher to give you the impression that these are legitimate. And the entire process looks so routine and normal that many times employees clicks on this accept button without giving a second thought. And once they do that, they are unknowingly authorizing a malicious cloud application created and controlled by an attacker. And once they click on the accept, grant their consent, then one OAuth access token would be generated, and using that access token, these applications can call various APIs provided by Microsoft or Google, and they can go and access your resources. Let's see how it can happen. So there is a cloud application or a client application which could be malicious. They send an authorization request to the resource owner, the user. They will see a consent screen like we saw in the previous slide. Once the user grants the consent, one OAuth access token would be generated by the authorization server, and these applications use that access token to call the resource server via APIs, and they gain access to your protected resources like emails, files, etc. And this is the concerning part. These applications do not need your password. All they need just OAuth access token. So even if you realized something has gone wrong and you go and change your password, that's not enough. What you will have to do, you will have to manually go and revoke those tokens. And I work for a team where our job is to build data-driven solutions, the machine learning solutions, to detect these malicious cloud applications. And over the period of time, we have realized traditional methods are not enough. And in this talk, I'm going to talk about what are those limitations, why we need to move towards the graph-based approaches. We'll have a quick overview of a couple of approaches we have developed, like risk propagation in the graph neural network. We will take a look at the results from the real-world attacks, and we will have some takeaways, and we'll conclude the session. So what are the traditional methods? So the first step is the data. We collect raw signals from a wide range of data sources. Now, these data sources could be registration logs of those applications from the Active Directory, the sign-in logs, API calls or the activities done by these applications, the details of the publisher or developer of these applications, or even features extracted from the URLs associated with these applications. And once we have these raw signals, what we do, we go and compute a broad set of features. And these features are effectively designed and developed in such a way so they can capture applications' behavior. For example, it could be how many and what kind of API calls have been made by these applications in past 24 hours. It could be how many users have successfully granted consent to these applications. Or it could be age, name, or some kind of other patterns in the application's data. And once you have these features, there are two traditional paths to detect these applications. So the first is the heuristic-based detection rules. These are nothing but manually defined logic based on a combination of features. And whenever that logic is met, they will go and flag applications as suspicious. The other way is to go and train machine learning models, typically in the anomaly detection setup. So what these ML models do, they basically try to learn the baseline patterns or the normal behavior from a set of clean or benign applications. And whenever they see an application deviating from that normal behavior, they will go and flag those applications as suspicious. Now, these works really well in many cases, but they do come with a lot of limitations. Let's see what are those limitations. So we have plotted the data for a few applications. You can see some features. These features could indicate the activities done by these applications, basically the count. And we also have the output from the ML models over traditional methods. Now, whenever we see these applications exhibiting high usage patterns or clear anomalies, our methods are so good, they will go and flag them as suspicious. But whenever these applications are inactive, dormant, or stay under the detection threshold, our methods would miss them. And this is the core limitation. These methods are often threshold dependent. So whenever attacker creates a large number of applications to distribute the load, and stays under the radar, stays under the detection threshold, or if the apps are dormant or inactive, our methods would not detect them. But if we zoom out, we start to notice something interesting. Initially, these applications which were undetected, they seem unrelated, but they do share some kind of entity with the known malicious or flagged suspicious ones. So in this case, you can see the application domain is common between these applications, and we have consistently seen evidences of these patterns in real-world attacks, where attacker creates and launches multiple applications, and these applications in smaller groups share some kind of entity between them, which could be name of those applications, URL of those applications, domain of those applications. And that's where the traditional methods fall short, because they are looking and analyzing these applications in isolation. And what we need to do, we also need to understand how these apps are connected with each other or other applications. And that's where we need a different perspective, where we go and build solutions which not only look at the individual features of these applications, but they also see how these applications are interconnected with each other. And that sets us the motivation to go and build a graph-based structure. So let's see how we can create this graph. So we start with a set of applications. Now, these applications are not just all the applications we have in our telemetry. These are the applications which are known malicious based on prior security investigations, or it could be the flagged suspicious ones from our traditional methods. And we call it the seed applications, which is basically the input to the graph creation. Then we go and extract the metadata of these applications, which could be your domain, URL, or your name of the applications, etc. So to give you the idea, or if you recall the previous slide, the seed applications would contain all the applications from the previous slide which were flagged malicious or suspicious by traditional methods. And after we add the metadata, we go and expand the graph, where we look for more applications which are sharing the same metadata, but they were not flagged, or they were missed by our traditional method. So again, to reconnect with our previous slides, the applications which were missed, which were dormant or inactive, they will be part of this particular set, because they did share the application domain with the previous or the left side of the applications. And once you have this graph structure, you can actually understand how the malicious applications or the flagged suspicious ones are connected with other kind of applications for which we have no information. And once you have this structure, what you can do, you can apply graph-based risk propagation. And these risk propagation techniques, what will do, they will flow the risk from the left side of the applications towards the right side of applications. And using that knowledge, you can go and say which one could be more risky and which one is more likely to be benign. Let's see how it can happen. So we start with the list of seed applications, and we assign the risk score of these applications between 0 to 1. And you know, like, these applications are known malicious or highly suspicious. So their risk score would be generally set close to 1. Then we add metadata nodes and assign their risk score as 0 because it's unknown to us. Then we add other applications which are unknown and comes under the graph expansion, and again the risk score would be 0 because it's unknown. And that's where the risk propagation begins. And for that, we have designed and developed 2 custom risk propagation scoring methods to propagate the risk from the malicious ones to the unknown ones in more precise and meaningful manner. So the first method, what it will do, it will propagate the risk from the known malicious ones, the left side of the applications, towards the middle layer, which is the metadata nodes. And the second method will propagate the risk from the metadata nodes, which is the middle layer, towards the right side of the applications, which are the unknown ones. And they will go and update their risk score. And now using that updated risk score, you can filter out what could be the additional set of applications which are highly suspicious. They were inactive, they were dormant, but they did share some kind of metadata with the malicious ones. And these scoring methods are not just statistical. We have developed them in such a way that they contain heuristic weights and the domain expertise, so we can minimize the noise while we propagate the risk. So for example, there could be a single domain which is connected to only one malicious ones, but a large number of unknown applications, so its risk score would be adjusted downward. So this is how we can apply the graph-based risk propagation, and we can identify additional set of malicious apps. Let's see how this really works in the real-world attacks. So this is the structure we get from a known malicious campaign which contain malicious OAuth applications, and this is what we get where you have multiple malicious apps and see how they have their own metadata. And once we go and expand the graph and apply the risk propagation, we can identify a new application which were undetected earlier, but it did share some of the metadata with the known malicious ones. And by applying graph-based risk propagation, we were able to identify 21 additional applications. And upon investigations, we confirmed that these were created by the same threat actor. And in that case, the common metadata we observed were application domains, URLs, or the names of those apps. And all of these applications remain undetected earlier because of their low levels of activity. Now, it's not the single example. We have consistently seen the output which helped us in detecting many applications in more and more campaigns. So there was another campaign where applications were abusing the user subscriptions, and we found out 41 new applications using this approach. In another large-scale campaign, we started with few applications, and we discovered 2,000 plus applications by using the risk propagation. So we put this model into production around 2 years back. And it gave us significant success. But like any other detection, it came with its own limitations. Let's see what could be the limitations of this architecture. So this is one example from a real-world attack where the attacker created multiple applications in such a way that the name, URL, and the domain of these applications were entirely different. So even if I know that, okay, A1 is bad, I cannot connect that applications with the remaining 4 ones. And in that case, the risk propagation even applied, it will always remain isolated because there is no common properties between these applications. In another case, we looked at 2 applications, and attacker, what he did, they used the slightly varied naming conventions. So if you see here, the name of the applications are quite similar, app 001, app 002. Now, to human eye, it will look very similar, right? But the graph will treat them as separate nodes, and you cannot go and create connection between them. And that's where, again, even with the knowledge that one application is bad, we cannot identify the other applications. Let's take a look at another limitation. If you recall our previous architecture, there was one core design choice we had, that we always start with the seed applications which are confirmed malicious or always high risk, because we wanted to keep the graph very scoped. So what kind of problem it can create in the real world scenarios? So let's say you had 2 sets here. The first set is the known malicious ones or high risk applications. The second set is unknown malicious applications. They are missed by our traditional methods. We have no idea about them. Why it happened? It could be attacker is using a TTPs, which is our traditional methods do not recognize. We have no information about them. So what will happen? The first section of the apps would be part of our graph architecture because they will be part of the seed applications, and we can do the risk propagation and we can find out more and more apps. But the second part will never make to the graph. And there comes a main inability of the previous architecture. It cannot give you the emerging clusters of malicious applications. It cannot give you the set of applications for which I do not have any idea about, but by looking at them, we might say that they could be malicious. The another limitation is that risk propagation is good, but is it leveraging all the rich set of features we were computing for all cloud applications? No. It only considers a couple of factors, but it does not consider a wide range of features we already compute for the cloud applications. And now there is a need to evolve this architecture in such a way that we have a broad set of seed applications. It not only contains the malicious ones, but it also contains the other applications. Also, we need to ingest the behavioral intelligence coming from our features into that structure. Let's see how that evolved architecture would look like. So the process is quite similar. You start with the seed applications, but now this seed application contains a broad number or broad set of apps. So you can see the pink color. Those are the unknown malicious ones. And the green ones could be the clean or the benign applications. And again, we don't include all the apps here. We keep these seed applications in such a way that these apps are either targeting or accessing a specific workload. For example, it could be Exchange. So in that way, we still keep this graph limited. So the graph, based on the graph techniques, we can then learn the patterns of the apps which are trying to access a particular workload. Then in the same way, we go and extract the metadata. We create the connections. We add these metadata nodes into the graph. Then we expand the graph. Now, these expanded set of applications could be inactive, dormant, or they might be accessing a particular workload, but they did share some kind of metadata from the left side of applications. And then comes a key upgrade. We enrich all nodes with rich set of features we compute. So for example, for the cloud applications, you can have what kind of permissions they were requesting, what are their API usage patterns, what are their sign-in properties, their publisher details, their names, etc., etc. And once you have this graph architecture, what you can do, you can go and train the graph neural network to learn the powerful embeddings, which can bring the similar applications together. Let's see. So you started with the set of seed applications. You went and you created the graph. Then what you can do, you can go and train graph neural network in supervised or unsupervised learning setup. And once the GNN model is trained and converged, it's going to give you the embedding for each application. And embedding is nothing but the numerical representation. It's a compact vector which you can have for each applications and what it contains basically. So whenever the GNN is trying to learn the embedding, it's going to look at two important factors. So one, what is the neighborhood of each applications and what are their properties? And then it's going to look at its own attributes, its own properties, and by combining these two sets of information, it's going to learn the weights and optimize the weights in such that the embeddings for the similar applications would be and they would be near to each other in the embedding space. So for example, if we started with random set of embeddings where you can see that similar applications are in the same color, and once the GNN has been trained, the weights are optimized, their embedding would be in such way that they are near to each other in the embedding space. Even they do not share direct connection, but their neighborhood and their attributes are similar. So the GNN would consider them as the similar nodes or the similar applications, and you can bring them closer into the embedding space. So what are embeddings? They are nothing but a way to numerically represent a non-numeric entity, which could be text, image, or in this case, application. They are non-numeric entities, but you can numerically represent them. So let's see how intuitively, what are the embeddings. So let's take a look at these words. So you have doctor, nurse, hospital. You have car, truck, vehicle. Now you know that semantically these words are similar, and they appear in the similar context. So whenever these words are passed through some language model, the model would go and learn the embedding for these words in such a way that in the embedding space, they are near to each other. So you can see the car, truck, and the vehicle in the embedding space, they are closer to each other because the language model understands they always appear in the similar context. They would be near to each other in the semantic space. Even their structure or the spellings are entirely different. And this is important because if you recall, we handle a lot of text features, the names of the apps, the URL, or the domain. So what we have done, we have trained our own language model, and we have computed the embedding for these text features in such a way that applications with the similar names. So if you recall our limitation slide, the app 001, app 002, and app 003 would have similar embeddings. And what we do, this embedding would be part of the node attribute in the graph for each application. Similarly, you have the domains abc1, abc2.com. We compute the embedding, and again, they will go to the node attributes into the graph. So when GNN is going to look at, when GNN is trying to learn the weights and do the optimization using gradient descent, it's going to look at the application's node attributes, which is going to contain these application names, these domain properties. It's going to look at its neighborhood. What are the nearby domains, nearby URLs, nearby other nodes, and their own properties. So when it learns those embeddings, it will bring those applications together, even they did not share direct connection in the graph. So just to summarize, we start with a broad set of applications. We create the graph. We train the GNN. We handle text features. We compute their embedding and ingest back to the graph. And then you will get the final set of embedding for each application. Now let's see how these GNN embeddings has given us the output in the real-world attacks. So what you see, when we trained this GNN, we got the 64-dimensional vector for each application. And we projected those 64-dimensional vectors into a 2D space, which is what you see. In this figure, each dot is basically a cloud application. And each color is representing the class or label of that application. So for example, the applications with red color, they could belong to the same campaign. They will share the same class. You see the blue colors as well. These are the unknown applications. So we have no label information, or these are the unlabeled information, but we still see something there. We'll see. So if you look at the two big clusters in the center, what GNN has done, it has actually brought all the applications that were part of the same campaign into a one big cluster. And not only one big cluster, what you also see the orange color, there are distinct clusters which are separated but smaller. And they all belong to the same campaign. What could happen there? Applications in one cluster could be very different in the second cluster. They could have a very different name. They could be doing a very different kind of activities or different kind of API calls. So when GNN is learning the embedding, it only brings the applications together which are similar in the nature, even they do belong to the same campaign. And then, interestingly, you have few clusters of unknown applications. Now, these could be your prime candidate for further investigations, and these could be your emerging set of malicious applications, which you can go further, investigate, and maybe they can give you some emerging campaign which might be happening. Let's take a look at some of the other results to understand how we can do the detection of the malicious ones. So what you see here, the pink ones, they are the known application from a campaign. We know, okay, they belong to this campaign. And the blue ones are the unknown ones. So we do not have any labeled information, or you can think of in this way, when we were training the GNN, we did not pass any label information for these applications. So those could be part of your test data. And what GNN has done, it has brought these applications together without having the label information, because the attributes, the properties of these applications are very similar, the structural properties and their behavioral properties. In another campaign, we observed the same thing, where there are applications which are very near to the known app clusters, and using this close proximity, we can spread the same label to these unknown applications, and we can say these are also malicious. And we have multiple metrics in our system, like precision and recall, where we are measuring the efficiency of these embeddings and these clusters. But we also get few clusters And here also it's the same case. These applications belong to the same campaign, but they are still far from the known malicious clusters. And upon investigations, we found out it is because attacker has evolved the TTPs. It has changed some of the naming patterns. It has changed the activity patterns. So what we can do, we can go investigate them, and we can update the label of these applications. Once the label is updated, it will be updated again our seed set of applications. We can go and retrain the GNN, and now using that updated knowledge, you can again go towards the detection of the other applications. So how we can advance this frontier? There is one famous quote by one of our leaders. Attacker thinks in the graph while defender thinks in the tables. So it's very paramount for all of us to go and understand in a real world attack how multiple entities are connected with each other, which could be your applications, users, domains, URLs. And that's where the graph-based approaches are the key, because it's going to give you how all these entities are interconnected and coordinating with each other, and it can comprehensively help you to detect those malicious entities. We integrate AI to analyze the unknown clusters we get from these embeddings. AI agents can go into those clusters. It can generate the observations. What are the characteristics of those applications? It can help us quickly take the decision whether this cluster is a potential malicious or it's a potential set of benign applications. But awareness is always our first line of defense. The more we understand about these risks, the more we can protect our resources. So whenever we encounter such kind of a screen, we need to be cautious whom we are consenting to. And there are some of the tips. You can always closely have a look at the name of these applications. So what you see here is not O365, it's 0365. You should always take a look at what is the logo of this application, and you should compare whether it matches with the publisher information or not. You should take a close look what kind of permission these applications are requesting. And then only you should take action whether to accept the consent or decline the consent. At the same time, many teams in our Microsoft company are taking these steps to help users understand the risks associated with these applications at the consent stage. And this is how together we can move from reactive security to the proactive resilience. Thank you.